So I want to introduce Bernoulli's principle by looking over 3 cases and then considering an additional case where we change in pressure. But the first case I want to look at is, so you've got water in kind of like an open source pipe. The concept or base on this example is that the pressure is constant. But Bernoulli's principle can be true even if the pressure does change. And for this, I'm going to use fresh water. Fresh water has a constant density, and it's also considered an incompressible fluid, meaning if I have water in a finite volume, I can't squish the molecules and make them smaller, like I could with a gas. You can shrink the gas is compressible, water is not. But again, Bernoulli's principle could work for gas as well. We would treat the gas and the liquid both as fluids in the case of their movement. The equation, though, is there are 3 parts to Bernoulli's equation. There's the pressure, and I'll add the subscripts, I guess, at the end. There's the pressure of a system plus the kinetic energy of a system. And because this is fluids, you'll notice the kinetic energy equation, this will look very similar to 1/2 mv squared, but instead of the mass, I have the density, v squared. But this is the same thing as the kinetic energy, but in this case, it's for fluid, plus the gravitational potential energy of fluids. So, again, instead of the mass, I have the density, gravity, and the height. And what Bernoulli's principle states is all of these 3 things combined is constant for a system, which the way I'm going to have us be looking at this is the case of before and after. If I change some variable in the system. So I'm going to have this be the before case. We'll call our 1, and then this is going to be our after case. We'll label as 2, okay? And let's move our Bernoulli's equation up here, just so we have it as a reference. And we're going to look at the before and after case for this specific example. I'm going to say, let's say this is a just common household pipe. It's open to the air so that the pressure is standard as 1 atmosphere. So the pressure is going to be 1 atmospheric pressure, which if you remember is 1,100 or 101,325 pascals. We don't need to actually know that for this problem. It's going to become irrelevant, and you'll see why in just a second. But that would be the pressure, and the velocity of the initial velocity of the fluid is going to be 10 meters per second. We will need to know that. And then let's say that the pipe increases to a height of 2 meters. So this is going to relate to how we can make water flow uphill kind of thing. So the H, the final height, we'll call 2 meters, where the initial heights at ground level we'll call 0 meters, okay? What Bernoulli's principle states is that the pressure before, the pressure at 1, plus the density, 1/2 the density, the velocity at 1, which is our initial velocity, plus the density, gravity, the initial height, so the height at 1, that is all equal to everything in the case of 2, the after scenario. So P2 plus 1/2 rho V2 squared plus rho GH2. We can simplify this. If the pressure is constant throughout this system, these terms are the same. Pressure is P1 equals V1. I'm just going to subtract them from both sides, and I get rid of that term. If I factor out rho, the density from each term, you'll notice why it doesn't actually matter what the density of this particular fluid is for this system, because the pressure is constant. So the density is irrelevant. And if I look at the initial height of the system, if it's on ground level, its height is 0, so anything times 0 is 0, so that's also 0. I get a relationship that simplifies Bernoulli's principle quite a bit. So the initial velocity, or the velocity in the first condition squared, is equal to 1/2 the velocity in the second condition squared plus GH2, the height increase. And I can calculate how slow the velocity will be going as it enters the second scenario. So as it goes uphill, it's going to slow down. Why is it slowing down? It's going to lose kinetic energy because it's gaining potential energy. So I can solve this equation for the second velocity if I add or subtract GH2 to the other side, multiply 2 and take the square root. get V2 is equal to the square root V1 squared minus 2GH2. And I can plug this in. This is going to be the square root of 10 meters per second squared minus 2 times 9.81 meters per second squared. The height increase, which was 2 meters. My units become meters squared per second squared under square root. That'll be meters per second. So my units look good. V squared is going to simplify to 7.79 meters per second. So it came in at 10 meters per second. It's coming out at 7.79 meters per second. Again, this is in the case of the pressure is the same throughout this whole system. The second case we're going to look at is going to relate to what we would call the continuity equation. So you'll notice the height is the same. I'm going to go under the guise of the same as constant pressure. Not much is changing in this except for the diameter or the radius in the second tube is bigger. We can kind of see that. So I'm going to specify that the radius of the second tube, and so we'll call this one, again, the first case scenario, and this will be the second case scenario. The radius, or R2, is double that of R1. So it's 2 times R1. That's our only thing that we've changed about it. We're going to call the initial velocity coming in, so the velocity of the fluid at 1, still the same 10 meters per second. The continuity equation states that the cross-sectional area of 1, the velocity of 1, has to equal the cross-sectional area at 2 times the velocity of 2. So if I think about this, I can just kind of see what's going to happen. If I'm going at 10 meters per second in the case of 1, and I go into something that's wider, you can think of I can fit more particles at once, but they're not going to be going quite as fast. So the overall velocity of the fluid should decrease. And I'm going to relate this to, let's say the pipes are cylinders, so cross-sectional area would be that of a circle. So cross-sectional area is going to be pi r squared. For the case of A1, we're going to call this pi r1 squared. Okay, the velocity is just going to be V1. We'll plug in the 10 meters per second in a minute there. It's going to equal the area of 2, which is going to be pi r2 squared, but we know r2 is twice that of r1. So 2r1, all of that squared. So you'll notice the 2 is also being squared. So it increases by a factor 4, not 2. Pay attention to that. And then this is going to be V2, our new velocity. I can solve this for V2. If I do that, I get V2 is going to be essentially 1/4 that of V1. Well, if V1 was 10, so this is 10 meters per second, it's 5/2 or 2.5. 2.5 meters per second. It's how much it decreases. Again, this is the continuity equation. It's where we can apply the principles more simply because I'm not increasing in height. I'm not changing in pressure. So there's a lot more continuous constraint on this. The third case we're going to look at is where I want to stress that this is a bit of an oversimplification of the problem. It's still under the assumption that pressure is constant. In reality, a system like this, the pressure would change. It's going to be a little more integrated. But again, this is a before calculus version of a physical science course. So we're going to put some assumptions on this here. So for this case, I'm going to basically treat the first part like Bernoulli's principle. So but I'm going to break it into 3 steps here. So this is going to be the first case. Coming out of the incline, this is going to be the second case, and coming into the increased area is going to be the third case. So between steps 1 and 2, it's exactly like case 1. I have the pressure isn't changing. So I have P1 plus 1/2 rho V1 squared. And again, let's also assume the increase was 2 meters. The velocity at 1 coming in is 10 meters per second. Okay, all these are the same. Let's move this over here because we're not going to have enough space. So the pressure at 1 plus the kinetic energy at 1 plus the gravitational potential, there's no M in that, sorry, force of habit. Gravitational potential at 1 is equal to the pressure at 2 plus the kinetic energy at 2 plus the gravitational potential at 2. And the pressure is the same, so it cancels out in every term. The potential at 1 is 0. I get the exact same equation I had for velocity at 2. V2 is equal to the square root V1 squared minus 2GH2, which one, if you remember when we calculated, we got 7.79 meters per second. So that's true as it's exiting. When it's entering 3, I'm now going to apply this to the continuity equation. So if we remember the continuity equation from case 2, and we'll do under the same condition. The radius was doubled. So R3 is now going to equal 2 R2. We're just changing some subscripts around, but it's the same incremental increase. We should still get a fourth that of the volume. So the volume is being quartered. V3 is equal to 1 over 4 V2, which in this case, I'm cutting this 7.79 down to 4 as I have 1.95 meters per second. It's going to slow it down even more. So this would be under the case of applying both the Bernoulli and the continuity equation. So I want to also briefly talk about what happens when the pressure does change, because the whole premise, part of why I think Bernoulli's principle is so cool, we can make water counteract gravity. And the way we do that is by changing the pressure. So again, this is somewhat of an oversimplification, but the thermocline, so I know the image is small and kind of blurry, but the thermocline is a very good example. The thermocline is essentially what happens with, it's kind of an oceanic water cycle that is part of the El Nino cycle. So it's the El Nino Southern Oscillation cycle over the Pacific Ocean. The Pacific Ocean is the largest body of water across the globe. Its oscillatory ocean current patterns and wind patterns affect the climate across the globe. So the thermocline is very important because what it is cold, nutrient-rich water gets collected at the bottom of the Pacific Ocean. And because of the pressure difference, that water gets pulled up off the coast of Peru, and it mixes with the warmer surface water, and it gets, essentially, it creates algae, nutrient-rich water for the marine ecosystem life, which also feeds the birds. And then there's pressure increase and change that affects the wind patterns that can then affect the climate really across the globe, but particularly on those coastal regions. So we're going to look at it in this case, again, oversimplifying using Bernoulli's principle. So P1 plus 1 half rho V1 squared plus rho GH1. That's going to equal P2, and I'll explain what each part is going to mean in a second. P2 plus 1 half rho V2 squared plus rho GH2. Okay, so this is going to be the before the water moves and after the water moves, just to show the pressure difference required to pull that water from the bottom of the Pacific Ocean to the top, right? Because gravity is going to pull it down. There has to be a pressure difference enough to counteract gravity to get it to flow upwards. And we're going to look at this just in terms of potential. So we're going to assume before the water starts moving and after the water is done moving. So we're not going to consider the kinetic energy at all. We're just going to be looking at pressure difference and height difference. And we're going to approximate that all of the water is at the bottom of the ocean completely at a height of 0. This is not quite the case because it's really a thick body of water, but for the simplification of this example, we're going to assume all of it's at 0. So the pressure difference then, P1, I'm going to subtract this to the other side. So minus P2, which is I'm going to call my pressure difference, has to equal the density of the fluid, which we're going to use salt water for this. It's a little more realistic, though I know we're already simplifying a lot, times G times H2. The depth of the Pacific Ocean right around there is about 4,000 meters. The density of salt water is 1,025 kilograms per meter cubed. Gravity is still 9.81. I'm going to call this difference in pressure delta P. That's going to equal rho GH2. Let's calculate all this. I get delta P equals 1,025 kilograms per meter cubed times 9.81 meters per second squared. times the height of the 4,000 meters. I get a change in pressure required to pull this at about 4.02 times 10 to the 7 pascals. If we subtract atmospheric pressure from that, because remember this is change in pressure, standard atmospheric pressure is about 101,325 pascals. It's not much of a difference, so it's pretty much approximate for that. Which is actually within reason. This is actually expected. The pressure measured at the Challenger deep, which is like the deepest point, is about 1.1 times 10 to the 8 pascals. So it's significantly more increase in pressure. So this is because the pressure is so great down there at the bottom, and the pressure is a lot less at the top. It is able to pull that water up. Which is really needed. It's actually really necessary for healthy ocean life and a healthy climate.